Hello, my DevNation friends. Welcome to another Tech Talk. And if you're a Java developer just like me, you should be super excited about today's Tech Talk because we're going to have a great Java developer talking about the latest and greatest features of the latest versions of Java and, of course, Java 17. That's why I'd like to invite to the stage my great friend Gunnar. And if I click the right button here, it is.
Hey
Welcome,
there,
Gunnar.
Essen. Hello. Awesome. Thank you so much for having me on the show.
Oh, it's always great to have you here. And before we started the stream, we were just talking that Gunnar has on his background. I don't know if you can tell that on the right side of his screen. He has a bonsai
Yeah.
tree.
Right.
Yeah,
There you go.
yeah, but it's a Lego one, so he doesn't have to take care of it.
Exactly right. So it's made from Lego. I cannot mess with it. I can break it, but it won't die if I don't water it. So that's good.
Oh yeah, that's the perfect stuff for you to have on your bookcase.
Exactly right. Awesome.
Awesome. So, what have you prepared for us today, Gunnar?
Well, I mean, as you said, we are Java developers, right? And we are very excited about this new version of Java, which just came out a few weeks ago. And I'm always interested in the APIs. So, what can we do with a new Java version? And that's what I'm going to talk about some of the new features in the Java 17 API and in the versions leading up to Java 17.
Cool. Can't wait to see that. So,
All right.
without any further delay, live from Hamburg, Germany, and
Right.
Raleigh, North Carolina, USA, welcome to DevNation.
Alrighty. Awesome. So, then let's get started. Um, Again, welcome to this session, and it's called To the Moon and Beyond with Java 17 APIs. And well, when I was preparing that talk, I thought, well, I want to talk about Java APIs. It's easy. I will just compile the list of new and changed Java methods, and we can go through that list. So, Edson, what do you think? Should we do that? Should we go through that list and talk about each item? What do you think?
Well, we only had 30 minutes. I don't know if you have enough time
Right.
for that.
Could be pretty boring, right? That's what I thought. Maybe it's not the best idea to do it on that detailed level. So instead, I thought, well, every talk should tell a story, right? And that's the idea. So I want to tell you a story about Duke, the Java mascot, and he wants to travel to the moon, and he would like to use some of those Java 17 APIs, and they will help him doing that journey. So that's the mission for our talk today. Commit ourselves to achieving the goal before, well, in this case, it's not the decade, but this talk is out of landing Duke on the moon and returning him safely to the Earth. And now, I guess if you will have recognized it. Originally, John F. Kennedy said it when they sent man to the moon back in the day, and now we want to send Duke to the moon. So that's our mission for today. And I would like to tell you about 3 different APIs. So I would like to tell you about the vector API, which allows us to do specific computations very efficiently. I would like to talk about the foreign linker API, which we can use to access native libraries from within our Java applications. And lastly, I would like to talk about JFR Event Streaming for getting out flight recorders out of our JVM. A few words about myself. As I mentioned, I work as a software engineer at Red Hat. I'm the lead of a project called Debezium. It's a tool for change data capture. I've been speaking about it here at DevNation Live, so you may go back to earlier recordings to find out more about Debezium. There's a few other things I'm involved with, and one of the things is called JFR Unit, and I will tell you in just a bit what this is about. By the way, there also was a talk actually about this one here on the show already. All right, so let's get started and really let's get right into it. So Duke gets ready. He would like to travel to the moon. And well, of course, in order to get there, he needs to do some calculations in order to find his way. He needs to calculate his trajectory. And this is what he found out then. So he went, he did some research and he found out, hey, there's this vector API, and this could help me with those trajectory calculations. Now, if you hear about vectors, you might wonder, hey, wait a minute, isn't there this class called Java util vector? And that's right, we have that class in the Java API since the beginning of time, I would say. And this is not what this is about, right? So instead, it's about vector calculations. So what does that mean? What's a vector calculation? And to make that a bit more tangible, let's take a look at the JEP, the JDK enhancement proposal for adding this vector API to the JDK. And there it says, the aim of this is to introduce an API to express vector computations that reliably compile at runtime to optimal vector instructions on supported CPU architectures, achieving a superior performance. So now, what is a vector computation? And really, it's essentially a feature which all modern CPUs have. So it's instruction set extensions to Intel CPUs, to ARM CPUs, which essentially allow you to apply the same computation to multiple operands at once. So you do the same calculation to, let's say, 4 or 8 or 16 operands at once. And it gives you this nice parallelization speed improvement by doing that. And now, if you think about it, there's different means of parallelizing our code, right? So you could, for instance, think about just scaling out your application to multiple nodes in a compute cluster, what you would typically do with microservices, let's say. A second means of parallelizing our code would be just implementing some sort of multi-threaded application using multiple threads on the CPU, which do some concurrent calculation. And now here, this vector API, or SIMD, single instruction, multiple data, this adds a third means of parallelization for us, which we can use within our programs to parallelize computations. So that's what we would like to do. And now the thing is, until now, Java developers didn't have a good way or didn't have any explicit way for using those SIMD, those single instruction multiple data instructions. It was just not possible for Java developers. That being said, the C2 compiler, so that's the compiler in the JVM, which takes your Java bytecode and produces the native code, this one sometimes does auto-vectorization. So in particular cases, it recognizes it can parallelize the code, it can vectorize the code, and then it would emit those SIMD instructions automatically for you, but you didn't have a way for doing that, for using that API explicitly. And that's going to change with this vector API, which currently, by the way, still is in an incubating state. So keep that in mind. And there's 4 goals associated to that JEP. And the first one is, well, they want to create a clear and concise API. So this means there should be an API which lets you easily reason about vectorized computations. It should, for instance, make it easy for you to do computations on different vector length, different data types, and it all should happen in a uniform way. Secondly, it should happen in a platform agnostic way. So as Java developers, we are very spoiled. We don't have to think much. Does our code run on an Intel CPU? Does it run on an ARM CPU? Or does it run on RISC or whatever? And the same should go for the vector API. So also those vectorized instructions, we would like to access them in a platform agnostic way. And now if you think about it, if you wanted to use SIMD instructions before, you would have to use a language like C or Rust, which makes those capabilities available to you. But then, of course, you would also be bound to the platform. So let's say you were using Intel's SIMD instructions. Well, then your program wouldn't easily run on an ARM CPU. Whereas here in Java, we are suddenly actually in an advantageous position because we have this, or we will have this agnostic API, and this allows us to run and implement those vectorized computations once, and then the compiler will take care of compiling this down into the instructions of the specific target runtime. Which touches on the third point. So this should be compiled into SIMD instructions on x64. So on the Intel CPUs, we have extensions like SSE or AVX, and also for the ARM ARch64 architecture. There's instruction set extensions called Neon and SVE, and those should be usable as well. And lastly, there should be a means of graceful degradation. So if our code runs on some platform which doesn't support SIMD, or maybe we use some part of the API which isn't supported by native SIMD instructions on a specific platform, well, then we should fall back implicitly and automatically to scalar execution. And then, well, we wouldn't have the performance benefit, but we wouldn't have to adjust our code. Now, in terms of use cases, why would you want to use this? And I would say most of the use cases for this really apply at the library level. So you could think about, for instance, image or text processing. And there it's quite easily imaginable. Let's say you have an image and you want to raise all its color values for many pixels at once. You could easily think about doing this in a way where you apply the same instruction to multiple pixels at once. So this could be pretty easily doable. But then there's also things like JSON processing. So for instance, there's this library called JSON by Daniel Lemire. And this is a very efficient library for parsing JSON. And they can parse gigabytes of JSON per second. So that's really impressive. And currently, that's a C library, but they already do have an issue in that tracker for using this Java library or this Java API for doing the same SIMD optimized JSON parsing also in Java. So that would be very interesting also for us as enterprise developers. There's other things like encryption or machine learning. So let's say something like TensorFlow. This could be, for instance, now imaginable being built using Java, which is the key advantage I see of that. So we can get to use cases with Java where maybe we did not consider Java as a prime choice before. And those new APIs like this Vector API, they help to improve the situation there. Let's get some terms out of the way. So let's talk about a little bit of terminology. And there's, well, we have this vector. And of course, that's just essentially like an array of values, a container of values. And they have a type. So in this case, it's an element type of integer, 32-bit values in there. It has a number of lanes. So that's the number of elements which can go into this vector. So here we have 8 lanes. Together, this forms the shape. So in this case, it's a shape of 256-bit. So 8 lanes times 32-bit for each element. And lastly, there's what's called the vector species. And this vector species, this combines this shape with a specific type, so an integer in this case. So we have this species of an integer vector and 256-bit length. So that's the terminology. Now let's see how we can actually use this and how this API would look like in being used. First of all, to start with, here's a scalar computation. So we want to do this computation there, which you see, like something like C equals minus A to the power of 2 plus B to the power of 2. And we want to calculate this computation for many elements which come in to input arrays for A and B, and we want to write them back to C. And the scalar computation, though, that's pretty easy, right? So you would just iterate over that array, you would calculate that value for each element, and you would write it back to C. So that's how you would do it. Now, how does it look like with the Vector API? It's looking a bit more complex, maybe a bit intimidating, but you should not be afraid of it. So what is happening here? Well, first of all, we get this vector species here. So we want to have float values. And now, instead of referring to a fixed length, we use this special constant species preferred. And this essentially means it gives us the maximum length of float vectors which are available at that particular runtime environment. So, there might be different extension sets in play, and we will use the maximum length we can get from the particular runtime environment. We don't have to care about it. Well, then we need to iterate, of course, over our input vectors, or arrays in that case. And now we do this essentially in a stepwise fashion. So we want to apply the same vectorized computation to multiple elements from that vector at once. And this is why we get this loop-bound variable. So this tells us how many times can we apply this vector computation to the array. So let's say we do it 8 times at once, and the input array is 20 elements length, has a length of 20 elements. Then we could do 2 full iterations, right? And we would have a remainder of 4 elements, and we will see what we do about that in a bit. So that's the loop bound. Then we do our actual calculation for all those elements, so we which fit into one vector. So we load a vector from A, we load another one from B, and then we do this calculation, multiply, add, multiply, negate, and so on, and we write it back into the C array. So we do this as many times as we can. And then we do have this remainder. So in my example, we would have 4 elements left. And for those in this case, well, they don't fit into another full vector of length 8 in this example. So we do this scalar post-processing here. Now you might wonder, well, that's not great, right? That's it feels very redundant. It feels undry. We do the same, or we express the same calculation twice, once using the vectorized way, once using the scalar way. Is there any way to avoid it? And yes, there is. There is a way where you can just do the vectorized one, and you would apply some sort of mask to that last vector which you cannot fully fill. And then you would only get away with just doing the vectorized computation. The problem is, when I tried this out, this masked approach, it was very slow, and it didn't give me performance improvement. So that's why, for the example, I stick to this scalar post-processing. But I would expect with newer versions, and as this API matures, also this masked approach would be more and more efficient, and we would not need to do this. All right, so that's how you could go about this API in general. And now there's really a large API surface. So if you look at this, I'm not sure whether you can read it, but that's just methods from A to B, and there's many more letters in the alphabet. So it's a large API, and where there's vector methods defined for all kinds of use cases, exposing all kinds of SIMD instructions. So you should go and take a look at the API. It's really rich, but also it's manageable, so you won't be overwhelmed, I think. To give you another example of how this could be useful apart from this very abstract calculation, and this is this FizzBuzz example. So I'm sure you have heard about this. It's often used in some sort of hiring interview kind of scenario. And the challenge is, well, you have values and you step through those numbers. Now, whenever you encounter a value which is divisible by 3, you want to put out fizz. If it's divisible by 5, you want to put out buzz. And if it's divisible by 3 and 5, you want to put out FizzBuzz. So that's the challenge. And well, it's easily solvable using scalar computation. You just would iterate through it. But then, well, we could also think about how we could use the vector API for doing that. And now, well, I did what every good software engineer does. I adjusted the problem a little bit. So instead of printing out values, I said, okay, let me just print out magic or print out constants. So, for the fizz case, I want to print out -1. For the buzz case, I want to print out -2. And for the FizzBuzz case, I want to print out -3. And now, so with that form of the problem, how could we use the vector API for solving it? And the idea is, well, I can do some sort of blend operation, and I will tell you how this works. So the idea generally is this pattern of -1, -2, -3. It repeats after a while. So what we can do is we can pre-calculate vectors and masks which describe this pattern, and we just apply those masks essentially to our input values, and this will give us those values. So what we do is I pre-calculate those vectors and masks, and by the way, I need 15 of a length of 8, then this pattern will repeat. And now I will do at those positions, which, the fizz ones, I will do -1 into the vector, and I will do -2 for those buzz positions in the vector, and I will do -3 for the fizz buzz positions in the vectors. And then for the masks, at those values, or at those positions in the vector which have -1 or -2 or -3, I will put a 1, and otherwise I will just put 0. And the reason for doing this is there is this blend API, and I can use this blend API to propagate values from the original input value vectors into the output vector by applying the mask to those vectors. So what happens is, if there's a 0 in the mask, it will take the original value from the input vector. So it will take the 1, it will take the 2. But then if there's a 1 at the mask, it will take the value from this other vector. So -1 or -2 or -3, whenever there's a 1 in the mask set. And I apply this blend operation, and that will give me the desired output. And if I, then I ran some JMH benchmark for analyzing this, and it gave me those numbers. So it's quicker or faster by a factor 4, which is quite impressive. Now, the point I want to make here is not, of course, how can you go about implementing FizzBuzz, and there's, by the way, even smarter ways for doing it. The point is more, well, even such a mundane problem, and even maybe something in our enterprise, environment might benefit from this vectorized API. And I believe if you think about your problems in your everyday work, you will be able to identify problems which lend themselves to being solved that way. All right, and of course, we should also take a quick look at the native code, so just to make sure we understand what actually is happening. And we can take a look at the assembly using this compiler plugin called HSDis. You can find out about how to do this on my blog. For now, I'm just telling you, okay, this allows us to understand what are the CPU instructions which are run by the JVM in the end of the day. And now, indeed, we can, trace this back, and we will see it compiles this down, this blend call from the API. It compiles this down to this VP blend VB instruction. And if we read up on that, it exactly says what we thought it would do. It copies byte elements from the source operand to the destination operand, depending on mask bits. So it exactly is an simplified version of that blend method, and this is what gives us this nice performance improvement. All right, that's the vector API. So let's take a quick detour, and let me tell you how you can identify API changes by yourself. And there's a few tools which you can use for that. So first of all, there's this great page, javaalmanac.io, which allows you to compare all kinds of Java versions to each other. So that's a great page, and I really recommend it. There's another one which I built myself. It's the Adopt OpenJDK JDK API diff generator. So you can take a look at that. It gives a bit more detail about this information. And there's also this great page by Chris Newland called JEP Search. And this allows you to go through all kinds of JEPs and, for instance, find out, you can search by keywords and so on. And it tells you which are specific JEPs touching on some areas. So all those tools, they let you identify easily in which Java version something has been added, for instance. And also, by the way, the Java doc, as of version 17, it also has this new tab. So there you will also see right within the Java API documentation itself what has been added compared to earlier versions. All right, so let's talk about the next thing. So Duke used the vector API. He did his trajectory calculation. So, well, now he wants to understand how much fuel he needs. And for that, well, he went to the internet and he found there's a C library, which was developed by the NASA engineers back in the day. And it exactly does that. So he would like to use this NASA C library for doing this sort of calculation. Of course, well, Duke is a Java developer, right? So the question is, how can you use this C-based library to make those calculations? And this is where Project Panama comes into the picture. Project Panama essentially is a set of JEPs, JDK improvement proposals, which deal with integrating JVM and native code and improve the story there. There's a few JEPs related to that. There's the vector one, which you already saw. And there's the JEP 389, which deals with native API access. And this essentially allows you, well, to call existing native libraries, so as in the case of Duke, or you could also think about maybe there's some thing which you just can express better or more efficient, maybe using native code, maybe using Rust, something like that. And so you can move this code into native code, and you can then use the Panama APIs to invoke those libraries. How would that look like? So I just have a brief example of that, but it's not very complicated. So what you want to do first is so all this works with method handles. So maybe you have heard of method handles as a replacement for reflection. And those method handles, they also provide you with access to native APIs. And what you do is you get a lookup, which allows you to retrieve method handles. And then this lookup, you use it to get a method handle, in this case, just for representing this getPit method. So that just is a method from the POSIX API, which gives us the current process ID. And by defining this method handle, we have a way for invoking that method. And lastly, we can just invoke it, and we will receive the value from this native method. So that's quite easy, I would say. You just define some method handles to describe that method, and you can invoke it. But it gets even easier. There's this tool called JExtract. And this essentially helps you a little bit with generating some code. So the way that one works is you define essentially, or maybe you already have it handy, some header file. So in this case, you just define this method there. You call this JExtract tool and you apply it to this header file. And then it will generate some code for you, or it will generate all the code for you. And then what you need just to do is, well, you just call this method. And now this doesn't look any different from, any other method you would call in Java. And if you have been using JNI before, this is much more easier because, well, you get away with just without any native considerations at all if you just use method handles, or you use this JExtract tool, and it will just work with in basic header files. So that's much, much easier. There's an example repo by this engineer, and I have a hard time to pronounce his name, Sundara Rajana, I believe. I hope that's how you say it. And so he's an Oracle engineer working on that, and he provides a great list of examples which show you how to use the foreign linker API, for instance, to use Git or to use libcurl, to use SQLite, all sorts of interesting native libraries. And it gives you a very good understanding of how you would use this for interacting with native code from within your Java libraries, or Java applications, I should say. All right. I want to briefly touch on removed APIs. And there's a few things here on that slide. I will skip most of it. There's two things I want to emphasize. The one removed thing is, the Nashorn engine. So this, you can use it for accessing JavaScript code from your JVM-based applications. And this has been removed. It's a separate project now. So you have multiple options. You can either just pull it in as a regular Maven or Cradle or whatever dependency since Java 15. Or there's also actually another JavaScript implementation called GraalJS, coming from the GraalVM project, which you also could use. So, just removing this API, it doesn't mean we are having a hard time. We just can pull it in separately. Why would they do it? Well, there's always maintenance cost associated, of course, to keeping APIs. And sometimes it's better to remove something like those ARM-I activation stuff, which just isn't used at all, so you can just get rid of it. Or as in the case of the JavaScript stuff, it's maybe better to evolve and to develop it separately. So those things have been removed. And there's another few things which are scheduled to be removed, or at least to be made no ops. And one of them is the security manager. So that's a very interesting one. Well, that's quite heavily used, I would say. It's not exactly not used. So I don't think it could be removed, but the idea there as well, it could be made as a no op. So your code would still compile, but you couldn't use the security manager. It wouldn't do anything. So I believe this would be very interesting to see what alternative patterns appear, how we can go about those security considerations. Because the original use case, applets, well, that's not given any longer, but still, things like Elasticsearch, for instance, they use the security manager to implement plugin isolation. So we will see how the story goes with the security manager. But the point I'm trying to make, not only APIs are added, sometimes also things are removed, and we need to find our ways to dealing with that. Alrighty, so we got the vector API, we got the from linker API, and now the last API I wanted to touch on is the JFR Event Streaming API, and I'm a big fan of that. And well, what does this allow us to do? It allows us to stream flight recorder events out of our JVM. By the way, why would Duke want to use this? Well, he is on his way to the moon now, and he needs to send back telemetry data to the Earth. And this is, well, of course, his rocket uses the JVM, right? So he's using this JFR Event Streaming API to expose and send those telemetry data as JFR event streams. Flight recorder, I believe, Edson, there was a session about JFR just recently, right? So just briefly, it's a framework for troubleshooting and monitoring and profiling, which is built into the JVM. So you really should take a look if you haven't seen it yet. It's an amazing thing. It can tell you about allocations. It can tell you about method profiling. It can tell you about I/O events, locks, class loading, garbage collection, all kinds of things. So it's an amazing tool. And now what we can do is we can also stream events, JFR events out of the JVM. So that's the idea. And by the way, if you want to understand what JFR event types exist, so there's this nice page here from Tom Schindel in Austria, and he compiles those overview pages with all the JFR event types per Java version. So that's very useful. With the streaming, well, we can react and we can process those JFR events in real time. So for instance, we could feed those JFR events to things like a dashboard. Maybe you have an external dashboard and you want to show your garbage collection events there. So you can use JFR event streaming for exposing this information. Or you can do things like predictive analytics. So that's very interesting. It's a very interesting use case, I believe. For instance, what you could do is you could apply some sort of analysis to those JFR event streams, and you could, for instance, tell, okay, a full GC, a full garbage collection is going to happen very soon. You might recognize it because, well, GC events occur more frequently, or there's specific events which tell you, okay, a full GC is going to happen very soon, and you don't want to send web requests to a machine which has a full GC going on, because it would mean you would have a long latency, right? So you could use this information to tell a load balancer which sits in front of your application, okay, this particular node of my clustered application, it's going to do a full GC within the next seconds, so please don't route any requests to that particular node. And this would be very interesting for the user, because their requests would not hit a machine which undergoes full GC. How does the usage of event streaming look like? It's quite easy. There's, it's pretty self-explanatory. You have this recording stream API. You tell it there for different events you would just like to react into a particular way by recording, by specifying a method reference or a lambda expression. In this case, for those 3 events you see there, I'm just printing them out. But again, I could use this to send those events elsewhere, for instance. There's also the means of exposing a remote JFR event stream over a JMX. So this is a nice project by, I believe, Eric Garlin, one of the JFR developers, where he has with maybe 200 lines of code, he has this nice profiling application. So you can use this event stream for implementing those sorts of use cases. So definitely take a look at that GitHub project, and this tells you how to use this remote streaming API. So that's super powerful. And there's this thing called JFR unit. And well, we did have a session about that before, right? So the idea there is to use JFR events and JFR event streaming to do some sort of performance regression tests. So let's say you identify your application suddenly is doing much more I/O, or allocates much more objects than it used to allocate before for one use case. Then you could use those signals for implementing some tests, and you would fail those tests, for instance, and it would tell you, okay, this particular use case suddenly it's doing much more database I/O. So take a look into this and understand what's going on. So that's JFR unit in a nutshell. And so that's a project I built, by the way, I should say that. And it's a JUnit extension. And the way it works is, well, you specify particular JFR events which should be enabled. So in that case, I would like to enable the socket read event, and I would like to enable the socket write event. Then I do run my application, my code under test. So here, that's a Quarkus application, and I run, multiple web requests against it. And I need to have this synchronization barrier. So I want to await all the JFR events which have been produced by that code. And then I can take a look at those events which were created by this application under test. And in this case, I just sum up all the events which represent database I/O, which are recognized by looking at the particular event type, just recognizing or considering I/O on a particular port, which would be my database port. And now in this case, I want to fail this test if it allocates more than 480 bytes per request. And well, if I would recognize that, then I could analyze this, and I could take a look, for instance, in mission control, JDK mission control, and to see why is this happening. So maybe it's valid that it allocates more, or it does more I/O because it just does more. Or maybe it's actually a regression before, maybe I'm suddenly doing some stupid mistake like a 1 + n select. And this way I will be able to find out about this kind of problem before this code would be shipped to production. And again, I would recommend, if you are interested in this, refer to the earlier session, which tells you much more about that. And there's one more thing to mention in terms of runtime features, actually, and that's AppCDS, class data sharing. And actually, those slides got mixed up. That's weird. This one should be here. So AppCDS, what this is about is it's about essentially creating archives with class metadata. So when your application starts up, it needs to load all kinds of classes, of course, and this takes a significant amount of time. And with class data sharing, the idea is, well, we run our application, and then we take the loaded class metadata and we persist it in some file. And then when we start up the application for the next time, we can reuse this file. We can memory map it directly, so we don't have to load the classes actually. But we don't have to go through the class loading routine, I should say. Instead, we just can directly map the metadata as it was persisted from the last time. So you can easily do this. You can create those archives yourself, and it gives you a very nice improvement. And just to make some example there, so that's a demo I ran a while ago. And if you look at the right two examples, so that's back with OpenJDK 15. And now this application, it was also a Quarkus application. And without the CDS archive, the time to first response was 1.8 seconds. And on the right-hand side, you see with class data sharing, it was 0.8 seconds. So it was 1 second faster with the time to first response. So that's pretty impressive. Another example would be Apache Kafka. So I created a CDS archive for Kafka. Without it, it would start up in 1.5 seconds on my laptop. With CDS, it would start in 1.5. Without it, it would start in 2.4 seconds on my laptop. And now, well, you don't start up Kafka in production all the time, of course. There it doesn't matter. But for instance, it does matter during tests. So let's say you use test containers for starting up Kafka in your integration tests. Well, shaving off the second, that definitely is very worthwhile there. So CDS, it's a great feature, and there's not much involved with it. It's essentially almost free for you to have. It's very easy to produce that archive. It just takes up a bit of disk space, and then you have those nice startup time improvements. So that's a feature with a very good, ratio of effort and effort you need to put into, or price you need to pay versus what do you get out of it. Alrighty, and that's essentially what what I wanted to tell you. So Duke used those APIs. He used the Vector API. He used the Foreign Linker API. He used the JFR Event Streaming API to make his travel to the moon. And I hope I could tell you, okay, this is actually there's some really worthwhile improvements in the Java API. And now, every Java version update, of course, it's not only about APIs, it's also about other things. It's about language improvements, it's about runtime improvements. And really, well, apart from CDS, I was mostly focusing here on APIs. And now I know most people always want to hear about language improvements, and that could be its own talk. There could be multiple dedicated talks about specific language features. So I'm just going to tell you there have been great improvements also in the language front. So for instance, you have text blocks, you have things like records, which really let you trim down the code you need to express or you need to write for value types or record-like types. And there's things like pattern matching, other improvements. So I did a Twitter thread a while ago about those language features. So take a look at that, and you will also see there's many, many great language improvements. And also runtime, of course, garbage collection and so on. So really, there have been many improvements apart from the API. There's only so much I can talk about in one talk. And lastly, I wanted to touch on some of the contributions Red Hat is doing for the OpenJDK. So OpenJDK is an open source project, right? And there's multiple parties involved, Oracle by far being the biggest contributor. And actually Red Hat, and that's very cool, it's the second biggest contributor to OpenJDK. So that's really cool. And to give you an idea what's going on there, so there's a few really exciting contributions done by Red Hat engineers. I'm sure you've heard about those. For instance, there is the Shenandoah garbage collector, which gives you sub-millisecond pause times with your garbage collection on really large heaps. So you can have hundreds of gigabytes or even larger heaps, and Shenandoah will work very well with that. There were some very interesting improvements done in regards to native binaries. So if you are using Quarkus, for instance, and you compile down your application to native binaries, you will know about it. So now you also have, for instance, JFR event support. So let's say you have some custom JFR events. You now can also use them in your native binaries. There's debug support. So, I mean, obviously, debugging, that's very important. Before this contribution, you couldn't easily debug GraalVM Community Edition code, whereas now this is possible. There's a few other things. One I want to mention is Lilliput. That's done by another German Red Hat engineer, Roman Kenke. That's a very exciting project, which is about trimming down the object header overhead. So each Java object which gets allocated on the heap, currently it would have a header size of 128-bit, whereas with the project Lilliput, this will go down to 64 or maybe even 32 bits. So that will be a significant improvement in terms of memory consumption of our Java applications. And lastly, well, there's also an OpenJDK distribution, so I'm sure you're aware of that since Java 9, or let's say after Java 8, or even with Java 8, actually. There's different distributions you can choose from. They have different traits like garbage collection and so on. And, well, there is the Red Hat OpenJDK build, which also is now available for Java 17, by the way. So definitely check this one out. That's pretty much all I had. There's a few resources. So there's this JEP search by Chris Newland. So definitely I recommend that. You can take a look at my blog if you want to read more about the SIMD stuff. I got some other posts about some also features like Unix domain sockets, for instance. If you want to learn about the JFR unit project, you can find that on GitHub. And lastly, there's the Red Hat OpenJDK build if you want to run OpenJDK on Windows or on Linux. So definitely take a look at that one as well. And Edson, I believe that's it. I mean, I'm not sure whether we have time for questions. I will be very happy to answer them.
Yes, actually, we have some comments.
Oh, you're on mute. There you go. Yeah.
Oh, okay. I'm back.
Yeah.
And then, Sebi was mentioning that his favorite new feature are records. And Vladi mentioned that his favorite new feature is the pattern matching for switch expressions.
Right. I mean, so if if you speak about records, so you can see it in the middle. So that's just a git diff, and it gives you the idea. That's the code we had before. That's all the red code, and that's the code we have now with records. That's the green code. So it gives you a nice, just by looking at this example without looking at the code, it gives you a nice idea of how much boilerplate you can avoid with records, right?
Hmm. Yeah, and we have one question here. Vlad is asking about app CDS. If the app will run in a container, do we need to
Yes.
prepare the CDS archive inside the container, or is it enough that we use the same JDK on the host where the archive is prepared?
That's a great question. So you need to use the exact same version and platform for creating the CTS archive and using it, and for also the same class path order, by the way. So what that means is, so you should be able to do it on the host if you build on Linux and you create a Linux container. This should work. Whereas if you use, let's say, macOS or Windows for creating your images or your container images, then you could not create the CDS archive on your host because it would be a different platform. So personally, I would recommend to do it in the Docker file. You can do it quite easily there, and then you're on the safe side.
Okay, cool. Yeah, question answered. And we're out of time today. I would just like to thank you, Gunnar, again for another
Absolutely.
amazing presentation. And
Thanks.
and if you're watching this, of course, it is live right now, but we're recording, and you'll be able to receive an email with the follow up. And the session is going to be in our YouTube channel, so you can follow up later, even like watch it as many times as you'd like.
Right.
So, yeah. So, Gunnar, I wish you a wonderful day. And as I
Likewise.
said, you're always welcome here to DevNation.
Definitely. Thank you so much for me. This was, I know it was a lot, but I enjoyed it. I hope people enjoyed it as well. Let's see.
No, we all enjoyed, and we have some people thanking you. Yes,
Awesome. Cool.
always great as usual.
Thanks.
All right. Thank you. Take care.
Bye.